All right, so I just wanted to say a couple words about 3.3 before we continue to other setups. And so consider this LP, the maximum of z equals 2x1 minus x2, such that x1 minus x2 is less than or equal to 1, 2x1 plus x2 is greater than or equal to 6, and then x1 and x2 are greater than or equal to 0. We just want to kind of check this out. So let's see here. I'm going to go ahead and do a little sketch here in the x1, x2 plane. And I'm going to take a look at x1 minus x2 equals 1, right? Oops. Am I still going? I think so. I just had a blowout there. Okay. And then 2x1 minus x2 equals 6. Okay, so the first line, that's a slope of 1, right? Goes through -1. So it's going to look something like this, and it's going to come out like that. Whoops. Well, that's a line. Okay. This one, the easiest way to plot these is to cover one of these up and then see what the other value is. So for example, if x1 is 0, then we see that x2 must be positive 6. And then if x2 is equal to 0, x1 must be 3. So we see that 3, 0 is one of the points that the line goes through. Oh gosh. And then I'm getting little notes here from the computer. 0, 6 is another point. Okay, so we can put a 6, 3 down here. Do a quick sketch. Good. Now, that takes care of my boundaries. And then finally, if I want this to be less than or equal to 1, I can test 0, 0. And 0 minus 0 is less than or equal to 1. So therefore, for this line, 0, 0 is included in the line, right? So that means that the line or the half plane is all of this stuff, right? And then for the second one, it's greater than 6. So if I put in 0, 0, you see that 0 is not greater than 6. And so therefore, it's on the other side. Okay, and so then including the x1 and x2 is greater than or equal to 0 leads me to say that my region is just this region. Okay, now I'd like to take a look at my isoprofit line. Which means I'm going to convert z to a constant k. And so if I do that, k is equal to 2x1 minus x2. And then I'm thinking of x1 and x2 as like an x and y, right? And so if I move x2 over, I see that x2 is equal to 2x1 minus k. So I have the isoprofit lines have slope of 2 and an intercept of minus k, right? Intercept. Good. So the minus k means that you're going to be coming down here, right, to intercept minus k. With a positive 2 slope, this has a slope of 1. And so a slope of 2 is going to be more steep. And so let me put that in red. My isoprofit lines will look something like this, right? This would be like -4 or something, and -6. I come down here like this, right? And so what you're seeing is that you can go down as far as you want. This line over here just extends out to infinity. So therefore, you can increase k to whatever you want. We can increase k to anything, and still have feasible points. I could say feasible solutions, feasible points, right? So that means that the LP is unbounded. The LP is unbounded. So we haven't run into the case where we have an unbounded linear program. Good. Now, one question that always comes up is the following. Is it possible for the LP to be bounded? Well, maybe I shouldn't say bounded, but to have a solution even if the region, the feasible set, is unbounded, like our example. So let's take a picture again. So I'll go ahead and draw it down here. So down here we have this feasible set, right? That was all of this, and so this is unbounded. And so is it always the case then that the LP has to be unbounded? No, because if this had been a minimized problem, right, then in our line here, our minus k, what would happen if we were minimizing this quantity? Well, let's see. Would that actually have a solution? Maybe I'll leave that up to you. What I'm thinking about geometrically is that suppose our isoprofit lines went like this, and to minimize, right, that the line gets lower and lower. And so in this case, right, I'm not writing down what the actual isoprofit line is. I'm just saying that in this case, right, you can see that it's possible that the LP has a solution even though the region is unbounded. Okay, so that was the main point there. So the answer to this question is it is possible for the LP to have a solution even though the feasible set is unbounded. Okay, so even though your feasible set may be unbounded, you may or may not have a solution. Okay, all right, and the last question I just wanted to mention is the following. Suppose I've got a feasible set that looks like this. I'm going to go ahead and start with the same kind of a set here with this interior, whoops, between these two constraints. And then I'm going to bring in another constraint. I'm going to say, well, in this constraint I also want to be down below here. Well, do you see what happened? In this case, there are no points that can satisfy all the constraints, right? And so in this case, the feasible set is empty. And in this case, the LP has no solution. Okay, so let's review this about the linear program. So when we say we're going to maximize or minimize, you know, this quantity where we have a cost function times our x, such that, you know, we have a11 x1 plus a1n xn less than or equal to b1, and so on. Oops, let me not be too. Let's see, I'm going to have m1, that's what I'm trying to write, plus amn x n less than or equal to bm, with x1 through xn greater than or equal to 0. Okay, so suppose I've got this as my linear program. Then I want to mention what calculus says about this problem, right? So calculus says if we have a continuous function over a closed and bounded region in Rn, So in Calc 3, right, the Rn was just R2 or R3. Then F attains its max and min, global max and min. Okay, and we know where that is attained. It's attained where the gradient of f is equal to 0. Okay, so in a linear program, the gradient of f is just going to be c, which is not equal to 0. Sorry, my echo went off there for a second. Okay, so in an LP, the gradient is going to be c, and that's not the 0 vector. So that means that if we have a closed and bounded region in our N, we're guaranteed that we have a maximum or minimum. And so if the feasible set is closed and bounded, we have at least one solution to the LP. Okay, so that's kind of nice to know. If the feasible set is unbounded, we may or may not have a solution. If the feasible set is empty, of course, we have no solution. And so in the case, notice that we never will get no solution if the feasible set is not empty, if it's closed and bounded. Okay, I've said enough. So that's the end of 3.3, and now in the next video we'll go on to building more models.